Let's return to our investigation of the mass spring oscillator system. So an object that's attached to a spring on a frictionless surface has an equilibrium position, and an object released from rest starting with some amplitude vibrates, and we've guessed and confirmed that a good equation that describes motion as a function of time is equal to x equals a cosine omega t, or if you prefer, x equals a cosine the square root of k over m times t. And the period of motion is then 2 pi times the square root of m over k. So we can graph position as a function of time. That's just going to be a graph of cosine. So at time t equals 0, the position is positive a, and after half of a cycle, the position is going to reach negative a. At a quarter cycle, it's 0, so we have a graph that looks like this for one full cycle. There's t, let's write it like this. There's lowercase t equals capital T. When the time is exactly one full period, then we complete one complete cycle, and the graph, of course, is going to continue on. So what about a graph of velocity versus time? Well, to get velocity, we take the first derivative of position with respect to time. So v would be equal to negative omega a sine omega t. So a graph of negative sine. So now the maximum value, the greatest you're ever going to get from the sine of anything is 1. So the maximum value of the speed has a magnitude of omega times a. So we have positive omega a as the max speed and negative omega a as the minimum speed. So we can say v max is equal to omega a. And at time t equals 0, the moment you release it, we're saying you release it from rest. So speed starts out at 0, and then immediately when you let it go, it starts out moving to the left. So it starts out with negative velocity, and it has its greatest speed when it returns to the equilibrium position. So there's a quarter cycle. After half a cycle, the speed is back to 0. Why? Because it momentarily comes to rest when the spring becomes fully compressed. At 3/4 of a cycle, the speed has its most positive value of omega a. So that's when the object, it started here, half a cycle, it's over here, 3/4 of a cycle, it's back to the equilibrium position and now moving to the right. And then, of course, after a full cycle, the speed is back to 0 and that motion continues. If we want to graph acceleration, take the derivative yet again. Acceleration is dv dt, and there's v, so acceleration is negative omega squared a cosine omega t. So the maximum acceleration is negative omega squared a. We're going to return to that in just a moment here. So a graph of acceleration versus time is a graph of negative cosine, meaning right when you first release it, it has its most negative acceleration, negative omega squared a, and eventually reaches its greatest positive acceleration of positive omega squared times a. But the moment you let it go, the acceleration is negative, and the reason it's negative is at the moment you let it go, the force is pointing to the left, and acceleration as a vector is always in the direction of the force vector, a equals f over m. So you start out with the negative acceleration, and after a quarter cycle, the acceleration goes to 0. Now the reason the acceleration goes to 0 is at a quarter cycle it's at the equilibrium position, but at that point the spring is relaxed, and with a relaxed spring, according to Hooke's law, if F equals kx and x is 0, then force would be 0. So you know where we're going with this. We get a sinusoidal graph. So we should highlight this line. This vertical line represents one full cycle. So that's t equals capital T. We could put a squiggly on this line and say that's t equals half a period. And you can figure out then what these other vertical lines are, I guess a quarter period and 3/4 of a period. Okay. Now what if we had made a different guess? What if we guessed that x equals, how about a sine omega t? Then we'd have a graph of position versus time that looks like this. And after a quarter cycle, half cycle, 3/4 cycle, and one full cycle, it's back to the original position. But that must be only if we observe in this manner. We take an object attached to a spring, release it from rest when it's stretched, and let it go. Let it pass the equilibrium point. Let it get to the point where the spring's fully compressed. Wait for it to come back to equilibrium the second time, and at that moment hit your stopwatch and begin observing. Yeah, then at time t equals 0, the position would be 0, and a little while later the position would start to get these positive values. So your origin in time just determines what the graph is going to be for position as a function of time, and that's sort of arbitrary. In any case, if that's position, then velocity would be equal to omega a cosine omega t. So a graph of v versus t would be a graph of positive cosine. Here's another way to look at this. Since speed is the derivative of position with respect to time, it's also the same thing as the slope. So let's do this. Let's draw in a line that represents the initial slope to this graph. Well, initially this slope is positive, meaning the value on this graph is positive. At this point, the slope is still positive, but not as great in magnitude, which corresponds to that data point. And ultimately, at a quarter cycle, the slope of the graph for position is 0, which means the value of velocity is 0. So in a way, you can just think of this graph as a graph of the slope of the first graph. In that regard, then the graph of acceleration versus time should be representative of the slope of the graph of velocity. So here we're starting out with a slope of 0, so we have an acceleration of 0. Here, the slope is a little bit negative, and so the graph starts to go negative. The slope is most negative at this point, so that means the value of this graph has its most negative value here, and then on you go. If you plot the slopes, you can get the graph. So it's kind of arbitrary whether we say x equals a sine omega t or we say x equals a cosine omega t. We just need to come up with a sort of a conventional way to do it. And I think the most conventional way is to imagine to begin timing the motion at the moment you release it. So we'll stick to this expression. Oh, and by the way, we said we'd return to this equation. Well, remember what omega is. Omega is the square root of k over m. So negative omega squared is negative k over m. So if we make that substitution, the maximum acceleration is negative k over m times a, or I guess we should say maximum acceleration. That's minimum acceleration, isn't it? Maximum acceleration would be positive omega squared A. But notice what this is saying, that maximum acceleration is Ka over m, but I would have guessed that anyway based on a free body diagram of the block when it's in this position. The free body diagram, say there's a force governed by Hooke's law pulling to the left, normal force and gravity cancel each other out, and this force comes from Hooke's law, says F equals kx. However, the position at this instant is A, so F equals Ka, and acceleration is force divided by mass, so acceleration should be Ka over m. Yeah, that's exactly what we have here, Ka over m. So now that we can see the sinusoidal behavior very clearly of the mass on the spring, let's talk about how the way the energy changes from kinetic to potential and back to kinetic and so on. Actually, I think it's the other way. It changes from potential to kinetic to, here's what I'm saying. The block starts out at the equilibrium position. We pull it back to set it in motion, so at that point energy is stored in the spring and it starts out with potential energy. After a quarter cycle, the spring goes back to relaxed, and now this object is moving with some velocity, and so all that potential energy has been converted into kinetic. But it continues moving to the left until the spring is fully compressed, and for a moment the velocity equals 0, and the energy is all back to potential. So kinetic energy is 1/2 mv squared. Potential energy is 1/2 kx squared. And we should imagine not so much these special points, but keep it as general as possible and imagine the block when it's at some point somewhere in between a position where it's fully potential energy or fully kinetic. At this point, the mechanical energy is a sum of kinetic plus potential. So let's refer to this as point B in our diagram, and then let's give a point A to consider. How about point A is the point where you release it? So at point A, the mechanical energy is strictly potential, and it's the maximum value of potential energy, which wouldn't just be 1/2 kx squared, because it's the maximum value associated with the maximum position of x equals a, then the maximum potential energy is 1/2 Ka squared. So which do you think is greater? The sum of 1/2 mv squared plus 1/2 kx squared that describes the total mechanical energy at point B, or do you think the expression 1/2 Ka squared, which represents the potential energy at point A? Well, of course, by the law of conservation of energy, these have to be equal. 1/2 mv squared plus 1/2 kx squared, the energy at point B, has to equal 1/2 Ka squared, the energy at point A. We can cancel out all the 1/2s. Maybe divide through by K. No, let's divide through by M. I like that better. Then we get V squared plus K over M times X squared equals K over M times A squared. And let's solve for V. Let's use this expression that describes the law of conservation of energy as a way to get velocity. Now, we already have velocity as a function of position. If position as a function of time is described as x equals a cosine omega t, then velocity is just the first derivative of that. So it's negative omega a sine omega t, but this is velocity as a function of time. What we want is velocity as a function of position. Well, that's what we're getting by applying the law of conservation of energy. All we need to do is subtract K over M times X squared on both sides of the equation. So we go from step 1 to step 2 to step 3, which says V squared equals K over M times the quantity A squared minus X squared. So we're almost there. In step 4, we get an equation by just taking the square root of both sides, and we get V is equal to the square root of k over m times the square root of a squared minus x squared. Or if you prefer, you might notice this. You know what the square root of k over m is. That's the value of omega. That's the angular frequency for the mass on the spring. So you can say V equals omega times the square root of a squared minus x squared. So either expression is equivalent for describing velocity, not as a function of time, but as a function of position. Now let's double check this, by the way. If x is a cosine omega t, what happens if we substitute that for x in this equation? Then we get V equals, well, how about we substitute it in this version of the equation? So we get V equals omega times the square root of a squared minus the quantity a cosine omega t squared. This means V equals omega times the square root of a squared times the quantity 1 minus cosine squared omega t. But 1 minus cosine squared is sine squared, so we get V equals omega times a squared times sine squared omega t, which means V is equal to omega a, well, plus or minus omega a sine omega t. But we already knew that. So it seems to agree. Our expression based on the law of conservation of energy that gives us velocity as a function of position, when we plug in position as a function of time back into that equation, we get the familiar equation for velocity as a function of time. Now I need to ask a couple of questions as follow-up. Position the object at the equilibrium point. Imagine releasing it from rest at x equals a. And the question goes something like this. Where is the object located when the kinetic energy is equal to 1/2 of the total mechanical energy? In other words, when is the energy split 50-50 between kinetic and potential? Or here's another good question. Release from rest and ask, again, x equals question mark, but a different scenario. Not when is the energy split 50-50 between potential and kinetic, but rather what's the value of x when the speed of the object is equal to 1/2 the maximum speed of the object. You might be tempted in both cases to say, well, that position is just whenever it's halfway back to the equilibrium point. But that's not correct. So let's take these one at a time. Let's see if we can figure out what's the value of x such that the energy is half kinetic and half potential. So another way to express this idea, the total mechanical energy of the system, it is 1/2 kx squared plus 1/2 mv squared if the object just in general is at some point that isn't so special. If it's not at x equals 0 or x equals a, or even at the position x equals negative a, instead if our object is somewhere in between, yeah, then the energy is part kinetic and part potential. However, the total energy of the system doesn't change, and so another way to express the total energy is to say the maximum energy, or the maximum potential energy at the moment it's released. So total energy is either 1/2 kx squared plus 1/2 mv squared, or it's 1/2 k a squared. And so we're trying to ask this question, when is the kinetic energy half of the overall mechanical energy? In other words, when is the value of 1/2 mv squared equal to 1/2 of 1/2 k a squared? Does that make sense? I'm just substituting. So we can cancel out this 1/2, and oh, well, time out. I'm not so happy with my approach here. If the kinetic energy is half of the total mechanical energy, then that implies the potential energy is also 1/2 the mechanical energy, right? In other words, the energy is split 50-50 between potential and kinetic. So I suppose a better way to do this would be to say U equals 1/2 total energy. So 1/2 k x squared equals 1/2 of the quantity 1/2 k a squared. So I'm still going to cancel a 1/2. Divide both sides of the equation by k, that cancels out as well. So now we have x squared equals 1/2 of a squared. If I take the square root of both sides of this equation, we get x equals rad 2 over 2 times a, which is the same thing as x equals about 0.707, or I don't know, I'm happy rounding off and calling it 0.71a. So when the position is 71% of the amplitude, the energy will be 50-50 potential and kinetic. Let's draw this really stretched out so we can see the x-axis spread out over a broader range here. There's x equals negative a, and the spring is super compressed. There's x equals positive a. There's x equals 0. So where's the point along the x-axis? Let's see. That point is 0.5a. So 0.71 might be about here. Yeah, so when the object is right here, that's when the energy is such that the kinetic energy and potential energy are equal and both half of the total mechanical energy. Moving on, we posed another question. What's the value of x so that the instantaneous velocity is half of the maximum velocity? Okay. Instantaneous velocity is 1/2 maximum velocity. Maximum velocity is omega a. Instantaneous velocity, well, that was the point of this derivation we did based on the law of conservation of energy. There it is. The velocity at any instant as a function of position is omega times the square root of a squared minus x squared, and that has to equal 1/2 omega times a. Cancel out the omega, square both sides of the equation. A squared minus x squared equals 1/4 a squared. A little rearranging, and we get x squared equals 3/4 a squared. So in the end, we get x is equal to rad 3 over 2 times a. And that's roughly x equals, what is it, 0.87 times a, or 87% the amplitude. So there's another special point, not at x equals half the amplitude, not even at x equals 71% the amplitude, but here at x equals 87% the amplitude, that's when the velocity is half the maximum value. So that means if I take an object, stretch it, release it from rest, then it only has to travel 13% of the distance back towards the equilibrium point to reach half of its maximum speed. Now, why is that? Well, because the spring relaxes as it decompresses, and so most of the acceleration The largest value of acceleration exists in the first few centimeters of motion. The rest of the way back to equilibrium, the spring starts to become more and more relaxed, the acceleration becomes less and less, and so the change in velocity is much greater in the first few centimeters of motion. We can see that on these graphs of velocity versus time that we made earlier. Notice the velocity starts out at 0, and in this region the slope of the graph is not all that dramatic. The graph has its greatest slope in the first few moments in time, and so 13% of the way back to equilibrium, which is a quarter of a cycle, that's when most of the acceleration takes place. In fact, if I erase some of my messy work here, if we're just trying to find when is the velocity half of its maximum value, so if we cut the maximum in halves, we find it's not that far along down the time axis that takes place. So thanks for tuning in. I know that's a lot of information. In the next unit of study, we'll move on and investigate the simple harmonic motion of the pendulum.